Okay, before we start, I just want to confirm that you guys can hear me clearly. And you can see my screen in a second. Just type in the chat. Okay, yes, crystal clear. Okay, perfect, cool. Okay, perfect. As well as YouTube, you guys can just confirm with me if you guys can hear me. Okay, sorry, I was late. Just needed to go to the bathroom quickly. Okay, assalamu alaikum and good morning to everyone. Welcome to the inaugural lesson for grade 11 physics. For those of you who don't know me or haven't met me yet, my name is Abdullah Ali, and I will be your guys' physics tutor for the rest of the year. Okay, so I think my screen is frozen. I'll reshare it in a second. Okay, cool. So if you guys do have any questions during the lesson, today we'll be starting with the basics of vectors and Newtons. If you guys do have any questions, please ask them via the chat or ask them via the Q&A. Okay, the notes that I give you, the notes that are in front of you guys will be sent to you guys on a Google Drive, which will be available to you guys mainly by the night, or whenever we do the lesson by that night or that evening. And yeah, please be aware of the group description. The group description contains the Zoom link, it contains the Google Drive link, and it contains the YouTube link as well. Just give me 1 second. Someone is asking for the link. Okay, cool. So let's begin, right? Is there anything else? I don't think so. Okay, so first we're going to revise vectors. Okay, we're going to do the revision necessary to understand vectors. Then we're going to go into Newton's law. And hopefully next week we'll get to do some questions, right? Some more difficult questions. So let's talk about vectors. And actually the first thing we're going to talk about is tail to head method. Okay, used for consecutive, just 1 more second. Okay, perfect. Used for consecutive vectors, vectors that occur in sequence. Okay, so this example, we'll do it along this this axis, but let's just talk about tail to head method. So basically, with tail to head method, you're going to draw all your vectors, okay, from tail of first. No, sorry. From head of first to tail of next. Okay, so remember our vectors represent magnitude and direction. So the size of our vectors are important. So let's just draw 2 vectors. Okay, so I'm going to draw 1 vector and it's pointing down. So that indicates to me the magnitude of the vector and the direction of the vector. Now, if I want to draw the next vector, okay, I would have to follow head to tail method. So I would have to draw it from the head of the first to the tail of the next. So the head of the first, we call this vector 1. I begin to draw the tail of the second vector at the head of the first. So just about there, I draw my next vector, number 2. Okay, and yes, magnitude is important. So the size of the vector is important. So in this specific case, we can see that 1, I think vector 1 is slightly bigger than vector 2. Okay, and we'll come back to resultant in a bit. So if they say, in this case, a boat travels 90 meters east. East is to the right, so we're just going to assume you'd have to use a ruler if you'd want to be accurate with your drawings, and you'd have to create a scale. So in this case, you could say that 10 meters represents 1 centimeter, sorry, represents 10 meters. So for every 1 centimeter, you draw 10 meters. Therefore, this we would draw 9 centimeters. So that's where the boat travels, and then it moves 50 meters north. So we move up 50 meters, and this would be 5 centimeters. Okay, so that's head to tail method for vectors. Okay. Let's look at this 2D vectors resultant and equilibrium. So we have something called the resultant vector. It is a single vector which has the same effect as the original vectors acting simultaneously on an object. Okay, so let's discuss that practically, right? If we look at this boat, right, this boat started there and it ended there. In order to get there, we went right and up. Okay. However, if we had, that was two vectors. Okay. If we had just gone from the start point to the end point, we would have had one vector. Okay. And actually, that is what we call the resultant vector. Okay. It is a vector that has the exact same effect as numerous two or more other vectors. So in this case, the 9 centimeters right and the 5 centimeters up could have just been replaced by this one diagonal vector. Okay, so that's what we would refer to as the resultant vector. And in fact, the resultant vector, there's a rule to draw it. So this is just for every vector. The resultant vector, however, is always from the tail of the first vector, like the very first vector, to the head of the last vector. Okay, always, always, always. The head of the tail of the first to the head of the last. So when you're drawing every vector, okay, not the resultant, the normal ones, you draw it from head of the first to the tail of the next. So head to tail to head to tail method, right? Whatever. But you just know that. So I cannot hear you. I think everyone else can hear me. Just double check your volume is up. Maybe restart your app or something like that. Okay. However, the resultant vector, that is from the tail of the very first vector to the head of the very last vector. Okay, so in this case, for example, if we had to draw a resultant vector, we'd go from, remember, this is number one. We go to its tail, head of the last one, which is there, and we draw it in that direction as well. So this would be the resultant vector. Okay, and here even the resultant vector. Okay, let's talk about Pythagoras to use the calculations to actually calculate the value, like someone said in chat that we use. Now we use Pythagoras. Now we're going to actually calculate the value of the resultant vector, or the distance in this case, as well as the angle at which it inclines. Okay, so here it's the same example, 90 meters west. And 50 meters up. So something like this. Again, if you're drawing it, your drawing would have to be accurate, right? So I'm going to call this 90 meters, and this is going to be 50 meters. Now, what is the question? Pythagoras can be applied to a vector triangles that are at right angles. Boat travels, determine the displacement of the boat. Okay, so they say the boat travels 90 meters due east and 50, and then moves 50 meters due north. Determine the displacement of the boat. If you guys remember from just like vectors versus scalars, like comparing the difference between displacement and distance, okay? Remember that displacement is the distance from the start point to the end point, okay? So if you go to the shop and come back home, your displacement is 0 because you started at home and you ended at home. Okay, but your distance would be the total amount that you travel. So let's say if the shop is 5 km away, so then you went to the shop 5 kilometers and you came back another 5, so that's 10 kilometers. Okay, so just keep that in mind. Displacement is the distance from your start point to your end point. So in this case, my start point is here and my end point is there. So they want me to calculate this distance here. Okay, which actually is our resultant vector. Okay, from the tail of the first to the head of the last. They want us to calculate that distance. So we draw in our resultant vector, and because one is perfectly east and one is perfectly north, one is vertical, one is horizontal, it creates a 90-degree angle, and thereafter we can use Pythagoras. Okay, so we call this guy resultant vector. We can say that the resultant vector squared is equal to 50 squared plus 90 squared. Okay, then when we do the calculation, we're going to say square root 50 squared plus 90 squared, and the resultant vector gives us an answer of 102.96. 102.96 meters. So now we know the total displacement of this boat is 102.96 meters. Okay, let's go back, and again we're going to talk about vectors in 2D. Okay, resolving it into its components. So the first thing is, let's just read what they say. Diagonal vectors can be broken down into components. When vectors are broken into the x and y components, we are determining the horizontal and the vertical effect of the vector. We can use sine or cosine provided that the angle between the force provided that the angle is between the force and the horizontal. Okay, actually just one more thing before we continue. So we know that this is 102.96 meters. If they wanted us to calculate this angle, we could have as well. Okay, by using trigonometry. Yeah. Do we have to round off to 2 decimal places? Yes, generally, unless they specify differently, you always have to round off to 2 decimal places. Okay. So in this case, we can use trigonometry. So we have the opposite, we have the adjacent, we actually have all. So we could use any of the trigonometric ratios. Okay. So in this case, I'm going to use tan. I know that tangent theta is going to be equal to, remember, tangent is toa, sohka toa, opposite over adjacent. So it's going to be 50 over 90. Okay. So that's the ratio. Because the angle is unknown, I have to shift tan. 50 over 90 to give me theta. When I do that calculation, I can actually get the angle. Okay, the angle of inclination of the displacement. Okay, and that answer gives us 29.05 degrees. So this angle here is 29.05 degrees. Okay, let's move on to our components. So resolving it into its components, right? Yes, it determines the horizontal and the vertical effect of the okay, let's just say we have a vector, okay, which could represent a force as well. That is a diagonal vector, okay, in this direction. So in this case, right, what will the direction be? For this one, yeah, the direction would be the displacement is 102.96 meters, okay, and the angle of inclination is 29.05. If you have to answer it on a bearing, okay, remember that the bearing is always from north. Okay, a bearing is always from north, so a bearing is there. All right, so the bearing angle would be from there to there. While the entire thing is 90, this is 29.05. This will be 90 minus 29.05, which is 60.95. So on a bearing, if they want you to answer it on a bearing, you would say, because remember, the bearing is always from the north end. So that's the angle on a bearing. So you would say that the displacement is 102.96 meters on a bearing of 60.95. Alternatively, if they don't ask on a bearing, you would say 102.96 meters, and the angle of inclination is from the horizontal, more specifically, is 29.05. Okay, no problem. Okay, so going back to our diagonal vector. Okay, now this diagonal vector is in the northeast direction. Actually, whenever we have a diagonal vector, we can break it down into a vertical and a horizontal vector always. So in this case, because the diagonal vector is, you could describe it very basically as up and right. Okay, your horizontal and vertical vectors would be up and right. Okay, so okay, maybe the sizing is not that great, but let's just resize it quickly. Okay, it would be something like that, right? I think I just drew the exact same thing, but okay. So yes, diagonal vector can be separated into its horizontal and its vertical components. Now let me show you how this makes sense. Right, remember we learned about the resultant vector, and we learned that the resultant vector is a single vector that can have the same effect as two or more vectors. So in this case, if I decide, okay, so I've just drawn them both on this Cartesian plane, right, on this set of axes. If I decide to do head to tail method, okay, and I say, okay, this is my first vector, and then my second vector, I'm going to move it from to the head of the previous. So the head of the previous is there. So I move it and I touch the head of the previous. Right now, okay, this diagram is not 100% accurate. Let's just redraw it, I suppose. Okay, that's not working with me, but something like that. Okay, so when you draw head to tail method, now you can see that vector 1 and vector 2 actually combine, okay, to create this. The diagonal force that we originally had alone is actually the resultant of our horizontal and our vertical. Is there a link to this document you are using for you to access it right now? No, but I will upload the document later. It will be on the Google Drive. The link for the Google Drive is in the group description. Okay, so do we see how this original diagonal vector is actually the resultant of 1 and 2 vectors? So that's why every diagonal force can be broken down into its parallel and into its, sorry, not parallel yet, into its diagonal, into its horizontal and vertical component. Okay, let's move it back here. And now it's on the axis. Okay, never mind. Let's just leave it alone. Okay, so that makes sense. So now we can see that we can resolve it into its components. So let's just do it again. Okay, now this time I'm going to keep it into the triangle. I know it's kind of skew, but one is horizontal and one is vertical. So that, what is going on, man? Sorry, my pen is bugging out. Okay, so that creates a 90-degree angle. Okay, so that's Pythag. Okay, so this is vector number 1, this is vector number 2, and this is its resultant. Right, and remember the resultant is actually the initial diagonal force that we had. We separated into its horizontal and its vertical components. Okay, because one is horizontal, one is vertical, again, it creates a 90-degree angle. So when we will call this angle of inclination theta, okay, we can represent, if we have this, let's call this F in this case, just say it's a force. I'm sure many of you are fine with that because you've started Newton's at this point, but let's just say it's a force. Okay, we can now represent the components in terms of the force. So if I want to represent, okay, for now, we'll just call this the opposite and we'll call this the adjacent. Or alternatively, we can use X and Y just like they do. So the horizontal, I'm going to call it X because it's on the X axis, and the vertical, I'm going to call it Y because it's parallel to the Y axis. So if I want to represent Y in terms of everything else, actually just in terms of F and theta, I will write that opposite over hypotenuse is sine theta. So sine theta is going to be equal to its opposite, which is Y, over its hypotenuse, which is F. Now, to leave Y alone, I take F over, and Y is equal to F times sine theta. Okay, we can even call it Fy if we'd like. The reason we call it Fy is because it's the Y component of F. Fx and xy, again, because it is the x and y component of that force respectively. Okay, so now in this case, yes, sine. If I want to represent Fx in terms of theta and F, I would have to use cos because it's adjacent and hypotenuse. Adjacent and hypotenuse. So cos theta is equal to Fx over F. If I want to isolate Fx, I say Fx is equal to F times cos theta. So these are firstly diagrammatic representations of the components of a diagonal force, as well as the mathematical calculations of a component. Okay, and then the resultant of two vectors be at a maximum. I'm not sure exactly what you mean by that question. Could you maybe rephrase it? Okay, let's move on. Let's talk about components on a slope. Okay, so when forces act on objects on a slope, it is useful to resolve vectors into components that are parallel or perpendicular components. The most common force resolved into components on a slope is weight, okay, which is Fg, which is gravitational force. Okay, the force of gravity. So firstly, we should note, and when we do free body diagrams in a bit, we should note that Fg, or gravitational force, is always downwards. Okay, gravitational force is always downwards. Now, in the case of a slope, the reason it is necessary to separate it into its components. So when I say components, I'm always referring to its x component and its y component, like we did here. Its horizontal and its vertical component, like we did here. Okay. Okay, so in this case, again, why it is necessary to separate it into its components is because of the slope. So if we just had a box that was vertical, and this box is on a platform, okay, the Fg would be straight downwards, okay, and while this is the planes are horizontal, okay, the surface is perfectly horizontal, okay, and the Fg force is actually perfectly vertical, okay. However, because the slope is now at a slant, the horizontal axis of our surface is actually slanted as well. Okay, when our surface is slanted, the horizontal for our surface is also slanted, and so too is the vertical. The vertical for our surface is also slanted. It also changes. Okay. So in this case, the reason it is necessary, you'll see when we do Newton's, is because you have to, in order to do the calculations, you need to have forces which are only horizontal, meaning parallel to the surface, or perpendicular to the surface. Okay, so you need to have forces that are either parallel to the surface or perpendicular to the surface. Okay, so that's why in this case we have to separate it into its components. So if we use this new axes, the x and y axis that we've created, we can sort of describe this Fg as a down left force, okay? And therefore it will have a down force and it will have a left force. Its components. The one on the x or the vertical axis, we can call it Fgx. And the one on the parallel, we can call it Fgy. I mixed them up, sorry. We call this one Fgy. Why? Because it is on the vertical axis. And we call this one Fgx because it's on the parallel. Okay, it's on the horizontal. Okay, sorry, I don't know why my pen is making random marks. Okay, so I hope that makes sense. All right, separating it into its components. just on a normal set of axes, and also separating it into its components on a slope. With respect to the actor and object resulting in two vectors be at the maximum. Okay, this is, I would say, when they're in the same direction. Okay, but I'll get back to your question in a bit. Okay, but yes, for now, that's resolving into its components and components on a slope. Okay, so now how do we get FG sine theta and FG cos theta? Okay, you'll see when we do Newton's, there's one generalization that we can make. However, for now, what we can do is we can use our diagram. Let's get rid of this guy. Okay, so our FG comes from the center, right? And it goes straight down. Okay, and now remember our components are going to be, our axes change. Our axes are here now and here because we're at a slope. And so too does our components. So because FG is sort of like a down left force with this respect, then we're going to have a down component and a left component. Okay. Now, how do we use maths? We have to always try and create that triangle. Okay. So I'm just going to move this down here. If I move my arrow down to complete the triangle, to draw head to tail, essentially, if I start from here, that's the tail of the first, and I go all the way, create the head of the first, right? Then from the head of the previous to the tail of the next, I create my next vector, and as you can see, the diagonal force in this case, which is FG, is going to be the resultant. Okay, so now I've separated into its components and created the triangle. So then that's where my 90-degree will be. Okay, and this is actually the angle we'll work with. And that's how we get FG sine theta and FG cos theta. Where will the normal force be? Okay, we'll get there in a second. So could you re-explain components on the slope? No problem. Let's go through it one more time. So we have an object on the slope. Okay. When we have an object on the slope, okay, so when we resolve into components, it is always for a diagonal force. Okay, always for a diagonal force. So we don't want to have a diagonal. What is the definition of a diagonal? Diagonal is based when it's not vertical or not horizontal. So here's my axis. I have the vertical axis going up and down, and I have my horizontal axis going left to right. Okay. Now, if I have a force that's like this, that is what I would refer to as a diagonal force. Anything that's not on these lines is a diagonal force. So that's why in this case, for example, this was a diagonal force and we separated it into its components. And then we created the triangle so that we could use trigonometry to solve for certain values. Okay, so we are doing the exact same thing here. It's just that now our axes are not how they normally are. Our vertical and our horizontal axes are also now diagonal, technically. The reason for that is because of the direction of the slope. The slope is at an angle. The slope is at an incline. Okay, the slope is now slanted, and therefore our horizontal always stays parallel to the surface. Our horizontal dotted line always stays parallel to the surface. So that's the direction of the surface. That's the direction of our horizontal. And therefore, perpendicular to our horizontal will always be the vertical. So the vertical is going to be that. Okay. Types of forces are exempted on the object that is sliding down the slope. Okay, we'll get there. right, when we do examples in newtons. Okay, so that is the reason why the reason as to why the axes are now slanted, because the horizontal needs to always be in line with the slope, okay, with the surface of the object, and therefore the vertical always has to be 90 degrees to the horizontal. So now when it comes to the forces, if we have to consider FG, now you might look at FG and say, oh, but it's a vertical force. It's not diagonal. Why do we have to separate it into its components? Correct. FGY is FG perpendicular 100%. Okay. So you might look at FG and say, but it's a vertical component. Why are we treating it as a diagonal component? Again, that's because we're not working with this anymore. We're not working with the normal axis. That has changed because of the slope. The slope is inclined. Our horizontal is also inclined. Our horizontal is inclined. Perpendicular to that is our vertical. So that's also now different. So now when we compare FG now to these axes, we can see that FG does not lay on any of these axes. FG does not lay on any of these axes. It's not up the slope, it's not down the slope, it's not bottom right, it's not bottom left. FG is now considered as a diagonal force. Okay, if we have to consider the direction of this diagonal force, we can see that it's down left. Okay, so when we want to draw its components, we're going to have one that is down and one that is left. No. Okay, so in that case, all right, we have FGY. So FGY will be on the y-axis. And FGX is going to be on the x-axis, right? FGY and FGX. Alternatively, we could call them FG perpendicular, or we could call them FG parallel. Now, why parallel and perpendicular? Again, it's with respect to the surface. Okay, so the one that's parallel to the surface, I know this is not exactly parallel, but just because my drawing is not perfect, but it should be, right? That's the one we call FG parallel, the one that's parallel to the surface. The one that's perpendicular to the surface, which is that component, we call FG perpendicular. Okay, and that's when we use head to tail method to move this guy there to complete the triangle. Okay, obviously now it looks a bit weird because I drew my FG parallel way too long. Okay, but yeah, it creates this triangle, and that is the theta that we work with here. Okay, sorry for the mess. Okay, but that's basically the components. So you can use FGX, FGY, or FG parallel, FG perpendicular. Okay, let's have a look at newtons. Right, and then the questions with regards to maximum resultant and types of force, I'll get to in a bit. Theta will be equal to the angle in the left corner. Correct. Okay, that is correct. We'll get there. Okay, let's look at Newton's laws of motion and discuss the different types of forces. So we have non-contact forces and we have contact forces. A non-contact force is a force exerted between objects over a distance without physical connection. So an obvious example could be magnets, right? Magnets could play an influence on one another without being in physical contact. We have electrostatic force as well as gravitational force. When we are on Earth, there's no string that's pulling us down. Okay, we just under the influence of gravity. Okay, so we always experience that gravitational force even without contact to anything. Then we have a contact force exerted between objects that are in contact with one another. So an applied force is us physically pushing or pulling something. Okay, and then tension, okay, which is has a rope attached to something that's in contact. Friction, when an object is in contact with the surface, okay, or the floor. That is a contact force that creates friction, as well as normal force, which we're going to discuss next, right? So normal force says the perpendicular force exerted by a surface on an object in contact with it. So remember, every single object in the universe is, or not the universe, every single object on this planet is under the influence of gravity. Okay, so there's a constant force exerting on us at all times. So if you have to consider your calculator or your pen or your paper or whatever it is on the desk, right? At any given time when it's on the desk, that is exerting a force on the desk. Okay, so let's just look at this. Let's just say this is a box. Now this box, you can see it exerts a downwards Fg force. Okay, downwards. Obviously, if it's downwards, it would be on the surface. So according to Newton's third law, which we will go through, Newton's third law states that every object in the universe exerts a force on every other object, okay? And that second object exerts a force back onto the first object, okay? That is equal in magnitude, but opposite in direction. So basically, this little box on the table, the fact that its gravity is exerting a force on the surface would also be exerting a force onto that object, back onto that object, equal in magnitude and opposite in direction. Okay, so in this case, we can see that Fg is down, F normal would be up, okay, because Fg is always down. Okay, so when an object is on a surface, the force that opposes that object's gravity is known as the normal force. And in cases where we're dealing with a basic example like this, like let's just say that this is an F applied. Okay, an applied force that's pulling this box to the right. We want to calculate its normal force. So firstly, we consider its Fg. Okay, so Fg is always down. And subsequently, in this case, F normal is up because we're on a flat surface. F normal is going to be up from the surface up. F normal. Now, when we work with F normal, right, we only consider, oops, one second. Okay, when we work with F normal, is Fg always down even with free body diagrams? Yes, that is correct. Fg is always downwards, even on free body diagrams, 100%. How will you get normal funds on a slant? That's going to be on an incline, which we will get to. What is F applied? So F app is force applied. Force applied. So any type of applied force. So in this case, it's a box on a surface, and there's an arrow moving to the right, which is indicating an F applied, yes, or FA, sorry. Many people just use FA, which is indicating a force to the right. So it's like a pulling force, right? Something is pulling this box to the right. Now, where were we? The calculation for normal force. I know that some of you might already have this understanding, this general idea where you want to say that F normal is equal to Fg perpendicular, okay? And you just want to generalize that all the time. This is completely incorrect. It's only correct in certain scenarios. It's only correct in certain scenarios, which we'll discuss. What is 100% true all the time, no matter what, come what may, rain, sunshine, is that the up forces in a diagram are equal to the down forces. Up forces are equal to the down forces. So whatever is up, okay, with that axis, vertical axis, and whatever is down with that vertical axis, okay, are equal to one another. So in this case, we have F applied, which is in the right direction. So that actually doesn't concern us when it comes to F normal, okay? So in this case, our up force is F normal. So we're going to say up is equal to down. Our up force is F normal. And our down force is equal to Fg. So in this case specifically, when does friction occur? We'll do an example of friction. In this case specifically, the normal force that's going up is going to be equal to the Fg that's going down. Okay, simply because that's all the forces that are going up. Don't we use the formula W is equal to M times G? Yes, correct. What force is Fg? Sorry, I didn't see this question. I'm not sure how long ago you asked it. What force is Fg? Fg is gravitational force. force by gravity. And to calculate FG, yes, you'd use M times U, which is mass times gravity. Okay, but for now, we're just discussing normal force. So yes, in this case, the normal force would be equal to FG. Okay, but that changes. Let's do one example quickly. On an inclined surface. Remember, the horizontal changes on an inclined surface. So that's now the horizontal axis. That's now the vertical axis. So remember, FG is here, which goes straight down. But now, in order to work with FG, so if I have to say up forces in this case, it would basically mean these forces that are up there, and down would be those forces. FG might look like a downward force in this case, but that's not the case because it is not in line with the vertical axis. This is not down in this specific case. When we talk about down forces, it's this guy here. That's the down force. Okay. So now in this case, I would have to say up forces and down forces. Now, that's the exact reason why I have to take FG and split it into its components. So remember its components, I can split it into a down force and an up force, always a vertical and a horizontal. Okay, where the vertical, we can call it FG perpendicular, and the horizontal, we can call it FG. Sorry, I'm going to get my pen fixed because I don't know what it's doing. We can call it FG parallel. Okay, so this guy is called FG parallel and FG perpendicular. Now, in this specific case, we have FG represented as a downward force. When we consider our F normal, in this case, let me just, nope, we cannot do that. Get rid of this for a second, right? So F normal, okay, in this case, would be always perpendicular to the surface. So if we look at the definition, a perpendicular force exerted by a surface. So this is always perpendicular to surface. This is the normal force. Perpendicular to the surface. So in this case, if we want to consider a force that's perpendicular to the surface, it would be in the upward direction in line with our axis. So perpendicular to the surface would be here. I'm just going to draw it from the center. Perpendicular to the surface would be that. So this is what we would consider our F normal. Again, it's not straight up because the surface is not flat. We are talking about perpendicular to the surface, considering more or less this is perpendicular to the surface. Okay. Now, okay, let's just fill in this guy again. This is FG parallel. So now when we consider, in this case, if we want to do the calculation for normal force, remember, normal force, the formula for normal force, you always have to use up is equal to down, meaning the up forces are equal to the down forces. So in this case, can somebody tell me what would we consider the up force? Fn, not FGY. FGY would be, okay, which FGY would be the down force. Okay, very good. Normal force, Fn, Fn, Fn. Brilliant, right? So Fn would be the up force, and then Fg perpendicular would be the down force. Okay, we must follow. So must Fn always be 90 degrees to the surface? Yes, 100%. Isn't FGY is equal to Fn? That is correct. So in this case, to calculate normal, we would say up is equal to down. So Fn is equal to FGY. Okay, and then FGY, okay, we'll get to that in a bit. Okay, let's talk about friction. Now, frictional force, okay, correct. Okay, frictional force, okay, so this is just basically to discuss the concept of normal force, and we've done calculations on a flat surface and on an incline, which is great. Okay, so when we get to the harder questions, when we get to everything in one, our normal force is done. We know how to calculate it. Okay, let's move on to friction. So always remember, for normal, up is equal to down. Don't make any assumptions for that. Okay, just up is equal to down 100% of the time. You need to have all your forces that are up, you need to have all your forces that are down, and you'll be able to calculate F normal easily. Right, frictional force. Okay, frictional force is so Fn is equal to Fg because the box isn't moving vertically, but rather shifting up the slope. So your second part of your sentence is correct. The box is not moving vertically. It's shifting along the slope. But your first part is incorrect. Fn is not equal to Fg. Fn is equal to Fg perpendicular because we are considering up forces and down forces. We have to say that the up forces should be equal to the down forces. So Fn is equal to Fg perpendicular. Okay. So yes, frictional force due to a surface is a force that opposes the motion of an object in contact with it parallel to the surface. So basically, if an object is moving to the right, the friction of the surface will always move it to the left. Okay, always opposite to the direction of motion. Frictional force is always opposite to the direction of motion. Whatever direction something is moving in, the friction will always pull it in the opposite direction. So friction is the parallel component of the contact force of an object by the surface on which it rests. The friction between contact surfaces is determined by the properties of both the contact surface and the object. Okay, that's important to understand. How much friction there is depends on what type of object you have, what the material is, and what type of surface it's on, what the material of the surface is. Okay, then we have something called the coefficient of friction. The coefficient of friction is a description of the roughness of the surface. So it's a coefficient, it's a set number for certain surfaces, and it gives us a description of how rough a surface is, how rough or smooth a surface is. The rougher the surface, the greater the coefficient of friction. Now we're going to discuss the difference between what about what? I don't understand. Just ask your question one more time, please, Mr. Hattie or Mrs. Hattie, or just Hattie. Okay, so firstly, we talk about static friction. Okay, now static friction is a frictional force on stationary objects, that's hence the name static, that opposes the tendency of motion of the object. The magnitude of static friction will increase from 0 as the parallel component of applied force increases until maximum static friction is reached. That's known as Fs max. And Fs max is the magnitude of friction when the object just starts to move. Okay, so then we have this force, which is Fs max is equal to mu s. Okay, the coefficient of friction, the symbol is known as mu. It's mu s times Fn. So in general, the formula here is that frictional force is equal to mu times F normal. Okay, when we deal with static friction, we deal with the static coefficient of kinetic friction, or the static mu, which is known as mu s. And then when we deal with when we deal with kinetic, which we'll learn in a bit, then we deal with the kinetic coefficient of friction. Okay, so that's the general formula. Friction is equal to mu times F normal. Okay, so let's discuss static friction for a second, right? Now, just say we have an object that is, could Fn also be written as mg? Yes, it could. Okay, just say we have an object that is stationary on a surface. Now, just because the object is not moving does not mean that there's not friction, because remember, friction is how rough a type of surface is. The more rough a surface is, the more there is friction, and also depends on the type of material the object is. Okay, we're going to end shortly. Now, when the object is stationary, just say it's about to move. Okay, but keep in mind that there's a certain amount of friction that exists between the surface and the object. Okay, so it's not going to move smoothly. If it was a frictionless surface, you just touch that object and it would move super easily. But now, because there's friction, when you push that object, you're actually going to have to push with a bit of force to overcome that friction. So initially, before the object even moves, the static friction is holding that object back. Okay, that is exactly what static friction is while it is stationary, it is holding it in place. So even when it tries to move, it will hold it in place until you obviously overpower that friction. So when you're trying to move the object, the static friction is exerted onto the object and is trying to basically stop it from moving. It's trying to oppose that motion. And then eventually you push and then it's not moving. Now, the friction is stronger than how much you are pushing. Then you push a little bit more and a little bit more until you actually start moving the object. That means you have overcome the friction. Okay. And that highest amount of friction just before the object starts moving, that is known as our Fs max. It's the magnitude of friction when the object just starts to move. Okay, then we have kinetic friction. Kinetic friction is the frictional force on a moving object that opposes the motion of the object. The magnitude of kinetic friction is constant for a specific system at all velocities greater than 0 and irrespective of the applied force. Okay, the formula could be Fk, which is kinetic friction, is equal to mu k, which is the coefficient of kinetic friction, multiplied by the normal force. Okay, so you see, that's also why it's important to know how to calculate normal force, because if you want to calculate friction, you need to calculate normal force. Okay, so basically we need to understand the difference between static and kinetic. So static is when the object is not moving. Okay, the surface still has friction and it will try to oppose the object from moving. And kinetic is when the object is already moving, and while it's moving along the surface, the friction still exists and it's still constantly trying to pull that object back, even though if it's moving, that means obviously that it's moving with a force greater than that of the friction. Okay, cool. So, let's just see our next topics. Well, for you guys, okay, I'm sure. So tell me something quickly in the chat. Are many of you still busy with Newtons in school? Okay, everyone. Yeah, I think everyone is still busy with Newtons. Okay, that's good. Okay, so it's taking a bit of time because we're going through all the basics. All right, but next week we'll carry on. So it's fine. By next week, you guys, you guys maybe should be on Newton's second law. Yeah, you guys should probably be on Newton's second law and doing free body diagrams, force body diagrams, and already doing questions. Okay, we are still by vectors. Okay, that's a bit behind. Okay, so yeah, so next week we'll continue. By next week, we will discuss all the laws and we'll get into a question, okay, doing free body diagrams, force body diagrams, and actually getting into a question, okay? If we do need to revise maybe some more on vectors, then we might do that. You're already on Newton's gravitational law. Okay, hopefully we can push through till there. You're writing a test on it tomorrow. That would be... You are done with Newton's, but you're writing a test on it. Starting on third law, we're doing equilibrium already. Okay. Okay, we're going to do as much as possible. Obviously, the tuition started a bit late, so we're going to try and catch you guys up to finish at least term 1 syllabus by your term 1 examination. Okay. Okay, yeah. So next week we'll try and get to questions. Okay. You guys practice, see how's it going. And then let me know if there's anything you guys don't understand and we'd like to do again next week as well. Inshallah. Okay, so yes, that's the plan. Next week, we're going to continue this, get as far as possible, get into questions, and yeah, be on the lookout for a timetable, hopefully by this week, so that you guys are aware of which topics we'll be doing at which times. And also, again, these notes will be available in the group. The link for the Google Drive is in the group description. The link for the link for the Zoom is in the description. The link for the YouTube live is also in the description. Actually, no, sorry. The link for the YouTube playlist is in the description. So if you'd like to go and watch the video again, you access it via the link in the description. How do you know when to use the static or kinetic frictional force? Okay, that's part of a question which we can go through next week. What type of forces are exempted on object when it's down the slope? We'll answer that next week. And then those two forces is back to the object control. Okay, I'll answer that next week as well, to the anonymous attendee who asked the question about the vectors. I mean, no problem. Thank you guys so much for joining. I hope that it was beneficial, and yeah, let's hope that we can pick up pace by the next week. Okay, we'll do still busy with the introduction of Newton's laws. Okay, I will send that link as well for someone who asked it. Okay, cool. Thank you guys so much for joining. All the best with your guys' week of school. If you're writing a test, good luck, and I will see you guys next week. Thank you guys so much.